Welcome, and it's also so nice to meet you as well. We didn't do a prep call or anything, and here we are.
Great, it's a pleasure to be here. Thanks, Jason.
Yeah, no, I'm excited. I mean, fusion is such an important topic, and it's a topic that seems to get climate Twitter up in arms one way or another. And there's a lot to talk about, probably well more than we can cover in 20 minutes. But we'll do the best we can to get the most meaty subset that we can. So for starters, maybe just introduce yourself and your company.
Yeah, perfect. Thank you. Hey, I'm Dr. David Kirtley, CEO of Helion Energy. And Helion's building fusion generators right now. Our goal is to get clean fusion energy out in the world as absolutely soon as possible. So I'm excited to be here to be able to talk about our technology, talk about my background, and talk about how we're going to get there.
Sounds great. Well, first things first, how did you come to work on fusion even before Helion? Like what led you down the path that you're on to begin with? Did you grow up as a little kid in kindergarten saying, I want to be a fusion expert when I grow up?
I remember I was a Navy brat, actually growing up in the military. One of us, places we were stationed was Bermuda, and I got to see the space shuttle actually take off and fly over top of Bermuda, and really got to show me what we can do with ingenuity and technology. So I got really excited, like how can I make real change? And energy goes right to it. And you look at fusion. Fusion is what powers the stars, what powers the universe. And I said, look, let me go figure out how to do this. Went to graduate school, spent a bunch of years learning about fusion, and said, wow, this isn't going to happen in my lifetime. And so put a pause on that and went and built rockets and some other things for a while. And it wasn't until I met up with the core team at Helion that was doing fusion a new way, what we call direct energy recovery from fusion, that there was a commercial path forward that made sense on a fast timeline. And so I went all in at that point and we started building prototypes as fast as we could, absolutely as fast as we could.
And maybe talk a bit, not a Helion specific question, but why fusion? If fusion works and we can commercialize fusion, so what? And I'm not saying so what to minimize it. I'm saying so what because I want to understand, like, what is the big promise if this works out as you and others that are working hard in the category are successful doing?
Yeah, as a human, well, I'm really excited by what's happening in fusion. The just explosion in the private industry space in fusion, the amount of capital going into private fusion is just it's so excellent and to see. And so I'm really hopeful of what I'm seeing overall in the technology space as well as the commercial space. And what it means is really important. Right now, here on Earth, the vast majority of our energy comes from the sun, heating, sunlight, solar, even fossil fuels originally came from fusion energy. But we haven't yet been able to harness it here on Earth in a commercially relevant way. And our goal is fusion has the promise of carbon dioxide free, proliferation free, so none of those geopolitical concerns, clean base load power generation. And that's what gets us excited. We're here in Washington State. We have lots of hydro power, a little bit of wind power. And we want to keep all of that we can, but as fast as possible, replace fossil fuels with clean fusion energy.
And one of the big knocks I've heard from critics is just that fusion is always 10 years away and it will always be 10 years away. So before we get into the specifics of the Helion approach, just where is fusion generally in terms of getting to commercialization, and what are some of the biggest barriers generally, again, before we get into the distinct approaches within fusion?
Yeah, it's we'll talk about Helion's approach specifically, but fusion in general, we have seen a whole variety of technology developments from in the not fusion space that allow us to just rapidly turn up the pace of building fusion machines. Advanced computing for Helion specifically, high-speed gigahertz fiber optics, large semiconductors that do high-power pulse power systems. Those enabled us to just leapfrog over generations of previous systems. And so that lets us really speed up. It lets us build prototypes. And then also there's a philosophy change, to be honest. The need for a real large scale, gigawatt scale answer to climate change is really pressing, and it's turning up the pressure on all of us to get these systems built. And so that allows us to iterate, just really focus on iterating quickly, building a prototype every year and a half, making large scale progress, and then learning what you can, retiring that system, go build a new one as fast as you can. And so there's a philosophy change. And some of this is driven by the Teslas and the SpaceXs of the world of how can you build hardware, prove new technologies as fast as humanly possible, because we have a real problem to solve. And so getting answers to those questions as soon as possible is really critical. And so we focus on technology, advanced fiber optics, advanced computing and simulation that allows us to jump over whole empirical steps, and then also high power semiconductors as a big enabling sets of technologies that have happened outside of our work.
And I'm far from a fusion expert, but another fusion entrepreneur who I spoke with a while ago, when he thinks about the landscape, I'm going to try to paraphrase, but there's a matrix of stuff that has less risk to get to commercialization, so maybe you can get to commercialization faster, but maybe it's more incremental progress. And then on the other hand, there's stuff that's like bolder and more disruptive if it works, but maybe it's higher risk or further out. How do you think about the landscape when you look at the different players and the different types of fusion that are being worked on?
Yeah, there's a lot of discussion in fusion of what are the metrics, what are the targets, what are you trying to build, and what are you trying to get it to do? So we've probably all heard of you want more fusion energy out than you put in. And there's recent systems now, big government programs that have showed that you can do that. But what we focus on at Helion, what we're doing behind me, is focusing on building systems that are commercially practical from day one. So everything we're going to talk about, the Helion approach, the technology, the hardware, it's all about making electricity. And that's our goal. And so even today, our goal is to now, we built 6 fusion prototypes, showed some really great technical and scientific results over the last few years. And now it's time to start talking about electricity and how we're going to get electricity out of fusion and on the grid. And so one of the analogies I like is the sort of the earliest electric cars were invented in the late 1800s. Sort of wild to believe that in 1890 there was electric prototype cars driving around, but we didn't have the batteries, we didn't have the transistor, hadn't been invented yet, we didn't have the computer equipment we need, we didn't have regenerative braking like we do in a Tesla now. And so you need all of those systems to take a technology that was theorized as that's the best way to make a car, but we don't know how to do it in a practical way. So we have to go through the whole generations of the internal combustion engine to get back to electric cars. And what we really needed was that the ancillary technologies to be able to enable those systems. And so that's what we do at Helion is we make sure, can we build systems that are small, can we iterate quickly, and then can we get to a system where we can get to electricity before anyone else.
And maybe talk a bit about the origin story for the company. When did it start? How did it start? And then I know we can't go through every detail since there's a long history, but just what are the different seasons or chapters that have led us to today?
Yeah, it's funny, that analogy, that old electric car analogy is kind of a good one in that some of the earliest concepts around fusion in the 1950s and 60s were very related to what Helion is actually doing now, the systems we build now, where we do what is called pulsed magnetic compression. We build systems where we have a high temperature plasma and using large magnetic fields, we squeeze that fusion plasma down. We showed we can get over 100 million degrees, 10 times the temperature of the sun, and do that repetitively over and over and over again, tens of thousands of times in a system right now. And the goal is, but those were theorized before the invention of the transistor. And it's sort of amazing to believe what our predecessors were able to build. And it wasn't until now that we can have large-scale systems that can commute gigawatts of peak power, that we can build them repetitively, safely, they work all the time, reliably, and then actually demonstrate a lot of those physics of the beginning. So in the Helion worked on a lot of work for the Department of Energy, NASA, DARPA, some other government agencies doing early stage research. We were able to build some small prototypes in 2008, 2010 that did fusion. We said, wow, on a tabletop, it was a bit bigger than tabletop at this point.
And was this with building a company in mind, or what was the motivation to do that initial work?
At that point was saying, hey, there's these theories of what people said we should be able to do. The technology finally is here. Let's go build them. Let's see if it actually works. And some things we were right, some things they were wrong, and we had to evolve that. but we were able to do that and build these systems that in a small laboratory anyway, we could do fusion, exceed 1 million and then 10 million degrees in these fusion plasmas, start really doing fusion, and said, wow, these small scale systems for a much less money, we can actually build quickly. They do fusion. Let's go start scaling and see where the limits are. And at that point, we said, great, we have this sort of proven basic research, and I cannot, thank enough the U.S. government's funding of basic research for these programs. But that allowed us to leapfrog right into private investment in 2013. Spin off Helion, and then just go building prototypes, big scale prototypes as fast as possible.
And you talk about how there were some components that in the first go around with your predecessors didn't exist that have been kind of a secret door, if you will, or a skip 5 moves in a board game as a kid or something. What are those parts, and how did you come about piecing together what would consist of the Helion solution set?
Yeah, even in my own career, when we started building these subscale systems, we weren't able to build the big ones. We were looking at trajectories of technology saying, okay, well, you can't buy that now, so we're going to try something very hard and very expensive to sort of leap to just get it built. But we see the projections of where it will be. And so with some technologies, high energy capacitors, relative to batteries that store all the electricity, fiber optics. When we started building these things, kilohertz fiber optics, so that operate in the millisecond time scale, was common. But now you can go to Best Buy and buy a 10 gigabit fiber optic network. And that allows you to control these fusion fuels on the time scale of the plasma, finally, on the scale of the fusion fuel. And then also the high power switching. Before, it was things we had theorized. And then as we start to build our prototypes and scale them, we could buy them custom. And now we can start buying off the shelf. And then eventually you can start buying knockoffs of these systems and start thinking about how you're going to commercialize and build many tens of thousands of these generators. And so that's how the technology has evolved, and it's been really great for us to be at that point where the technology and all the ancillary supporting requirement technologies all grew together at around the same time. We couldn't have done what we were doing 20 years ago. None of the supporting equipment existed at that time.
And I know you mentioned that the first private capital came in 2013. You've raised a lot of money at this point. Maybe talk a bit about the funding that you've done to date and the key milestones in each. And that might not be the most intuitive way to talk about milestones, but that's kind of what I'm after, is the chapters of the company.
Yeah, so in 2013, when we spun off Helion, we were able to go out and raise a Series A and then a Series B, which was on the order of $30 million in those two fundraisers. That let us build some small scale prototypes, start scaling up the systems.
That's like a Fusion friends and family round, right?
That early work was mithril capital, but yeah, on the scale of Fusion, it's on that scale. In contrast with our last fundraising last year, which was about $500 million in cash, and then another several $1 billion in commercialization funding that unlocks when these systems turn on and start making electricity. Our goal is to start demonstrate we can make electricity in 2024, and so that's what the current system is. We call this one. This is our 7th generation prototype. We call this one Polaris. We used to name them after Starbucks, Tall, Grande, Venti, but we ran out at some point. They got too big.
And when you think about staging, so what were the most important things to de-risk in the early stages? And then what are the most important things to de-risk in the stage that you're in right now?
Yeah, so some of the earliest things to de-risk, we haven't talked about technology too much, but this idea that we're going to directly take the fusion energy as electricity, we're going to extract that. That was one of the first things we had to show, is could we build these really high efficiency modern power circuits? And so that's one of the things we built in 2014, was showing we could do that and do it at really high efficiency. In fact, the efficiencies of our systems we demonstrated were over 95% efficiency. That means if you can build fusion systems that efficient, everything else gets smaller, simpler, the physics gets easier. But you still got to do fusion. And so our third, fourth, fifth, and sixth generation prototypes were scaling up the actual fusion reaction, scaling up the temperature. And then so that in 2020, we're able to build full-scale fusion system that's at a 50 megawatt scale generator, in scale anyway, operate it for a little short periods, but get over 100 million degrees, 10 times the temperature of the sun, run it for over a year, and really show the key physics, some of the key engineering. But it wasn't running steady. It was really demonstrating physics. And so now we're building our seventh generation system that's to now take that physics that we demonstrated, tie in a lot of the engineering from it, recover all the electricity from it, and then for the first time in 2024, generate electricity.
And so between now and 2024, what is left to de-risk, and then what happens after that? What does the staging and phasing look like if you're successful?
It's a really good question. We got a lot of work to do between now and then. And so what you're seeing behind us, we're in our facility in Everett, Washington, which is north of Seattle. And right now behind me is our first fuel injector system. So this is a large scale, multi-meter long fuel injector that'll go into Polaris, which we're building in a building that's adjacent to us, that I can't take you to today because we're doing foundational concrete work there. But that's where we're going to build that first generator. So some of the key de-risking things, we have to keep turning up the power. We showed that we can make a lot of fusion reactions, a lot of energy from these systems, but not that we would cover electricity from it. So that's the first thing we got to do, is take all those advanced circuits we've built, tie it with the fusion physics, recover electricity, so you can do that for the first time, and then start reparating this system. Great, you did one pulse. We demonstrate typically about a pulse every 10 minutes for an afternoon or an evening, every evening when we do fusion. But we need to actually turn that up and start running not every 10 minutes, but every 10 seconds, every once a second. So we can start generating not just a little bit of electricity, but large amounts of steady electricity. And all kinds of engineering shows up when you start doing that. All the thermal engineering, reliability engineering. And so we're massively growing our engineering team to support this.
And when you say commercialization, who is this for? Who might the customers be? How involved have they been in the process to date? And what's the business model for you or for any fusion company for that matter?
This is a super great question. And I don't think if you asked all the fusion companies out there, I'm not sure you would get the same answer for each of us. Helion wants to build generators. We want to site them, and we want to actually sell that electricity. So that's our goal. And early customers are private customers that are interested in large amounts of power. They want it to be as clean as possible. So we think data centers and some other sort of big industrial customers that want clean, really exciting technologies, get them out there and get them off of the diesel generators and the other systems that they use today, the really dirty systems they use today. And so there's a good business model overlap. There's a good requirements overlap. And so those are your first couple of customers. But eventually we want to go as fast as we can to get out large-scale baseload power. That means power utilities. That means generation capability.
And for that initial customer set, what's the pitch? Is it a cost pitch? Is it a performance pitch? Is it a collective good pitch that they should do it because it's good because it's the right thing to do? Why make the move?
Yeah, so it's you can't win without cost, so you have to be able to answer the cost question. So we'll touch on that in a second, but it's also the common good that you have. We know that climate change is accelerating. We know that we need good baseload answers to provide power that's on all the time, especially as electric transportation starts taking off more, all of those things. And so being able to provide that power for those customers is really good for their end users, for example. But then also in parallel to that, you still have to be cost competitive. Simply having a good mission isn't enough. For power utilities anyway, or even most private customers of power. And so we want to be able to push as hard as we can. One of the beauties of fusion is that because the fuel is common deuterium found in all water on Earth, safe, common, cheap, you can talk about very low cost electricity, projections of few cents a kilowatt hour of baseload power generation. And if you can get there with a fusion system that's reliable and safe and running all the time, generating no carbon dioxide, then not only have you've won the cost battle, but you've also won the mission battle.
We're running out of time, but two final questions. One is just, we've talked a lot about the factors that are within your control and areas that you're trying to de-risk. If you could wave your magic wand and change one thing that is outside of your control that would most accelerate your progress, what would you change and how would you change it?
Yeah, it's a very good question. I think in the world right now, one of the things that we worry about a lot is a lot of the supply chain. We worry about we have to source a lot of equipment from overseas. We source it all throughout the United States. I mean, we're building as fast as we can manufacturing internal in Washington State. But what's going on in the world? Like to accelerate fusion, the more that we could do to get large-scale capacitor, large-scale semiconductor manufacturing, and there's been some really interesting legislation that just happened around this, which is really exciting for us too. And get those in the United States, get large-scale manufacturing. That would help us a lot. So we spend a lot of time thinking about how to de-risk the manufacturing part of this.
And last question, just for anyone who is attending the event and listening to this interview, who do you want to hear from? How can the audience be helpful to you?
Yeah, so the big thing I always want to point out, Helion's hiring. We passed over 100 people about a month ago. We are hiring best and brightest engineers. We're building something no one's ever built before, and so there's a lot of good work to do, a lot of exciting new ground. What I actually like to tell a lot of our engineers and scientists that join is there is no fusion textbook on how to build a fusion generator. Doesn't exist. The people that are getting into fusion today in this exciting field are the ones that are writing those textbooks. They're the ones that are writing the manuals for how to do fusion and how to get it out in the world.
David, thank you for this discussion and best of luck to you and the Helion team. I'll be rooting for you.
Thank you very much. It's a pleasure. Thanks, Jason.